Well, we're closing this first day with a Rick Hoadley from ABB. He's a principal consultant applications engineer, and he will be talking to us about variable frequency drives, which is a very interesting topic for motor manufacturers. So yes, this is the last presentation today, and whenever you're ready, thank you very much.
All right, very good. Again, thank you for hanging in here to the very end, right? All right, we'll talk about principally the harmonics which drives produce on the input side of the drive. And so we'll take a look at what's the drive system and line side requirements, harmonics, how to reduce harmonics, and that'll be really the focus of this discussion here today. So when we think of a drive system, we want to compare that to something else. This would be a non-drive system. Have a transformer that feeds some sort of a switch, and then that feeds the motor, and the motor's feeding the load. And when you take a look at what the motor sees, the motor simply sees a nice sinusoidal voltage. The current that it draws from the power line is a nice sinusoidal current. It's lagging a little bit in terms of phase because of the power factor for that. But other than that, things look real nice. But when you put a drive in there, things change. They change two ways. On the input side, what the transformer that's feeding the system sees, it's going to have to start providing pulses of current to that drive. And when it does that, the current no longer is going to look like a sine wave on the input side, and it contains harmonics. And we'll get into that some more. On the output side of the drive, it puts a bunch of voltage pulses out to the motor. And by changing the width of the voltage pulses and how quickly they go from positive to negative, that's how we get our variable voltage, variable frequency, as going to the motor to be able to change the speed and the torque of that motor. So the motor sees something different, the transformer sees something different, and that's what we're going to look at. So sometimes I like to almost start the talk with, okay, so if all these things, weird things come along with the drive, why do we use drives at all? If they're simply going to cause problems. And here are some of the reasons why. First of all, we have a large operating range for speed and torque. If you simply run a motor across the line, all you're doing is you're operating from here to here when you go from no load to full load. And here's your torque speed curve for that motor. But with the drive, you can operate over the whole green area at any speed, any torque within that area, plus, of course, a little bit of overload, and you can do that with the drive. You can't do that with a motor simply running across the line. Another reason is cost savings. This is a very big one, especially for fans and pumps, because how do you control the flow on a fan or a pump? It's usually with some dampers or valves or for inlet vanes, something like that. But whenever you use those things, what's happening is the motor's going to still be running at full speed, and the amount of torque that motor has to produce is still often close to full torque. And so you're putting a lot of energy into this system, and what you're getting out in terms of the flow is very little energy. And so putting a drive in there, by reducing the speed of that motor, you can reduce the flow, and by the same way, the torque goes down with that, and because the torque is a squared function, power is a cubic function, so if you're running at, say, half flow, the torque is going to be 1/4, and the power is going to be 1/8. 1/8 of the power. That's what you pay for, is that power. And so there's a huge energy savings there, huge payback. Usually within 6 months to a year, you've already paid for the drive. And after that, it's like free money. And everybody likes that stuff. Another is for optimizing a process. So you don't lose your whatever product you're making. And so you can adjust the speed to exactly what you need. Another reason for that is when you start a motor. And once the motor's going, everything's fine. But getting it started is usually the tricky part, because the motor's going to draw about 6 times full load current just to start it. And so this is what you would see if you're starting the motor across the line. Huge amount of inrush current, then it drops on down, then it continues on at say, full load. With a drive, the amount of current that you draw is like nothing. And it ramps up as the speed comes up, even though you're at full load torque on that motor throughout that whole time. And so for a soft system or generators or something like that, you're not going to drag that system down when you're starting a big motor across the line. This way, it's a nice gentle way of bringing the motor up to speed. So drives are great for that. Another thing is starting torque. You can get a lot more torque out of that motor using a drive than you can with across the line. Even though across the line you're drawing like 6 times current, you're not getting 6 times torque. You might get 100% torque. You might get 80% torque, maybe 120% torque, but not 6 times. Because the speed torque curve is like this when you're across the line. Even when you're starting torque is there. With the drive, you can get huge amounts of torque simply by setting the speed at the right point. The power factor. The power factor that you draw from your grid and through the power system is a lot higher, a lot closer to unity with the drive than it is with a motor running across the line. Motor running across the line, the best you can get, well, there typically is about 0.87, right? Maybe you might get up to 0.9, but not much better than that. With a drive, you can have power factors. Well, this one is with, say, an active front end, and you get unity power factor with a drive that has what's called an active front end on it. With just a diode bridge front end, it's still better than a motor. You're going to be up around maybe 0.9, 0.95, somewhere around there. So that means you can improve the fees you might have to pay for low power factor from the utility. And then also we have adjustable torque limit. And so you can control the amount of torque that motor is producing. And so when I talk about the mechanical jerk, that's not the derogatory term for the guy who was running this machine when that shaft broke, but it's a quick change in acceleration is what jerk is. And so things like this will not happen again if you have a drive on that motor. So when you take a look at a drive, you wonder, well, what's inside the drive? There's really 3 main parts. The first is a rectifier, then you have this filter, and then you have the inverter section. The rectifier is what takes the 3-phase AC, converts it to DC. You say, well, wait a minute, is this a DC motor drive or an AC motor drive? Well, it's an AC motor drive, but we start by converting it to DC. So there's DC inside that drive. And then we take that DC, we chop that up to give us a variable frequency, variable voltage going out to the motor. So those are the 3 key pieces for the drive. But in an industrial drive, something which you want to last for a long time, something where you want your motor to last a long time, you're going to have some filters on that as well. Filters on the input side to reduce the harmonics that the input rectifier is doing. Some filters on the output side so that you have a lower dB/T going out to the motor, which really helps improve the lifetime of the insulation system on the motor as well. So you can buy a real cheap drive, which is only this big, but there's no filters in that thing. And your motor's not going to last very long. It might be cheap, but you're going to have to buy another motor soon. So just because it's cheap, that doesn't make it good. So that's what drive systems are. Now, what about line side requirements? What we're going to take a look at is harmonics. And there's 2 aspects to harmonics and what's called Fourier transformations. There's a thing that's called analysis and another thing called synthesis. We'll start with the synthesis. We can create a waveform, a periodic-looking waveform that is not sinusoidal simply by using sinusoidal waveforms. And here's what I mean. Suppose we have a piece of equipment in a transformer, and you take a look at the current that this piece of equipment is drawing from the transformer. If the current looks like this, a nice-looking sine wave, then you know 2 things. One is that there's no harmonics in that current waveform because it looks like a sine wave. Or maybe there are some, but there's a very, very minor amount. And what we would call that load then would be a linear load. So sometimes you see that in literature. Linear loads is simply a load that draws sinusoidal currents from the transformer that's feeding it. Now, those types of loads would be things like this, like an induction motor like we saw before. Incandescent lighting, which it's getting harder and harder to buy, right? Resistance heaters, power factor correction caps. Transformers, sort of. Sometimes they can cause some harmonics, but for the most part, they're sort of like a linear device. But suppose I have this other piece of equipment hooked up to this transformer. It's drawing currents that look like this. Well, we know 2 things about this piece of equipment. First, because the current does not look like a sine wave, right? That's definitely not a sine wave. Therefore, we would say that that waveform has harmonics. It contains harmonics. And we would call this a nonlinear device. So again, if you see in the literature the terms linear devices, nonlinear devices, that's really all they mean. Nonlinear devices draw waveforms that do not look like sine waves. Now, what falls into that category? Well, say under three-phase, welders, arc furnaces, UPS systems, DC power supplies, like the power supply for your laptop. That's a nonlinear device. Take a look at the current going into that sometime. It's ugly. I'll show you what it looks like. But it's not totally ugly. It's kind of interesting, but it's not a sine wave. DC drives, AC drives, for single-phase, fluorescent lights with the ballast, incandescent lights with light dimmers, computers, monitors, TVs, compact fluorescent tubes. All of these are nonlinear loads, and they produce current waveforms that do not look like sine waves. Therefore, they produce harmonics. So when we talk about harmonics, there's really three parts to these things. The first is a frequency. Now, what we mean by that is the power line frequency is what we call the fundamental frequency, or the first harmonic. And all the other harmonics are really integer multiples of that. So here in the U.S., we have as our line frequency 60 hertz. And so 60 hertz is our fundamental, or the first harmonic. The third harmonic is going to be 3 times that, which is 180 hertz. The fifth harmonic is 5 times that, which is 300 hertz, and so on. Over in Europe, they have 50 hertz as their line frequency. And so, again, the fifth harmonic of that would be 250 hertz, and so on. Now, over in China, they have 50 hertz. I heard in New Zealand they have 50 hertz. I told my boss, hey, if I'm going to be talking about this, I think I should go there and actually find out, do they have 50 hertz or 60 hertz? And he says, no, you don't get to go. Look it up somewhere. Use Google. So, okay, well, I guess they have 50 hertz there, but I really don't know. Maybe check that out sometime for me. A couple places in the U.S., they've had 25 hertz power. And they're slowly getting rid of that. Because I know up near Niagara Falls, Niagara Mohawk went to their customers, a small industrial park where they had 25 hertz power. And they said, hey guys, we're going to have to shut down our generators, and we want to replace them not with new 25 hertz power generators, but with 60 hertz power generators, because you're the only ones that are using 25 hertz. And these generators are like 98 years old. You know, they're reaching end of life. And this industrial park says, well, what are we going to do? You know, I mean, if you simply switch over everything to 60 hertz, so it used to be at 25 hertz, that means the elevators are going to go real fast, which is kind of scary. And the assembly lines are going to go kind of fast, and the lights will be okay. That's fine. So what they actually did for that is they used drives where they feed the drive 60 hertz, and they simply turn the frequency on the output of the drive down to 25 hertz, and that would feed the rest of the plant until they eventually switch everything over and they get up to speed with 60 hertz as well. In the train system over in Europe, they use 16 2/3 hertz. It's like 1/3 of 50. So interesting frequency. Airplanes use 400 hertz. So 50 and 60 hertz isn't the only thing that you see around the world. But for now, we'll stick with 60 because we're here for now. So that's the frequency aspect. But there's also an amplitude for these harmonics, and there's also a phase angle for these harmonics. And we'll see how these all play together. So here we'll start with 60 hertz. So here's a fundamental current. It has a peak of 100 amps, and so the RMS value is going to be 100 divided by square root of 2, so that's about 71 amps. All right? And we see that at time t equals 0, it starts right at 0, so it has a phase angle of 0. I'll show you what a fifth harmonic looks like. Here's a fifth harmonic. You might wonder, well, how do I know it's a fifth harmonic? All we have to do is count how many cycles are there of that within one full cycle of that fundamental. So if we start right here, you know, one cycle of the fundamental goes from here to here. So if we start right there, we go, here's 1, 2, 3, 4, 5. There's actually 5 cycles of that, so we know it's a fifth harmonic. The amplitude, we can see the peak of it, it works out to be about 28 amps RMS. And then for the phase angle, well, we say it's 153 degrees. Well, it's sort of like, where is it within its cycle when the fundamental is at 0 degrees? So, you know, we have 0, we got 90 degrees there, 180 degrees there, 270, and then back to 360 or 0 degrees for one cycle. So 153 degrees is a little bit before you reach 0, but you're heading downward, and that's what's happening right here. It's at the 153 degree point right there. So that's a 5th harmonic. Let's take a look at another one. Here's a 7th harmonic. How do I know it's a 7th harmonic? Let's count them, right? So starting right here, we got 1, 2, 3, 4, 5, 6, 7. So sure enough, it's a 7th harmonic. We can measure the amplitude. It's around almost 11 amps RMS. And the phase angle is about 282 degrees. So it's a little bit past the peak negative point. And that's where it's at right here. So it's starting to come up towards 0 there. And let's show you one more. Here's the 11th harmonic. How do we know it's the 11th? Yeah, you can count them, right? I'll let you do that. And it's about 5.5 amps RMS, and it's at 0 degrees. So it's starting right at 0 at time t equals 0. Now let's do something interesting with these 3 harmonics, that 5th, the 7th, and this 11th. Let's add those guys together. So, well, how do you add them together? Well, each one has an amplitude or magnitude at any point in time. So all we do is just add them up, just like we add normal numbers. So, like right here, we add this value to that value to that value, and see what, and put a dot right there. Go to the next point in time, and put, you know, just dot, 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 dot all along there, and here's what we get. We get this blue waveform. That's a sum of those 3. And it's interesting looking. It's kind of like a sine wave, but it isn't, right? Because the peaks are varying now. Where a sine wave, they don't change like that. And it's got some interesting lumps in there, which, but that's the sum of those harmonics. Now, what I want to do is I want to add a few more harmonics to this thing, all right? So like a pinch of the 13th and a dash of the 17th and a little bit of the 19th and so on. And so I get this. Not too different from what we had before. If you close your right eye, which is clearer, this or this? Yeah, you know, eye doctor always tells you to do that, right? I always think he's trying to fool me, and I don't know, something. But anyway, so all I've done is added a few more harmonics to this. So it just made some things a little bit sharper. But now let's do one more thing with this. We're going to take that blue waveform. We're going to add it to the green waveform. All right? And let's see what we, right before we do that, if we wanted to figure out what's the RMS value of that blue waveform, what would it be? Well, you wouldn't want to use a peak or the maximum or the minimum here. Somewhere maybe halfway in between. If it's like 50 amps, the RMS value of 50 amp peak is around 35. So maybe 35 amps RMS. That's just eyeballing it. But we'll check that out in just a minute. But now what I'll do is add that blue waveform to the green waveform, and what we get is this red waveform. And so that red waveform is really what you would see if you had like an AC drive attached to a transformer. You take a look at that current going to that drive, you would see a red waveform like that. And what that red waveform is made up of is that green waveform, which is the fundamental, plus all those harmonics, which is that blue waveform, as summed together. And you say, well, wait a minute. Is that red waveform really the sum of that green waveform and the blue waveform? And yes, it really is. Because look at it this way. Right here, on this portion, what we're doing is we're adding this bump right on top of that, and that's the reason why it bumps up right there. And right here, where it goes negative, we're actually subtracting that from the green waveform, so it dips down. We're adding another guy right here, so it comes up here. And here it gets kind of interesting, which is as interesting as this really gets, is where we're going from positive to negative. It's fairly linear along here on that green waveform. The blue waveform is going from negative to positive fairly linearly. When you add them together, you actually get 0 right here. They cancel each other out. So you get this red waveform that's got these 2 bumps to it. It's 0 part of the time, and we created that simply by adding some sine waves together. Isn't that amazing? You look amazed. All right. Now, what we'd like to do is let's do some analysis stuff. Usually, what you do is you start with that red waveform, and you want to find out, well, what is that red waveform made up of? And there's a way to actually accomplish that. This is called an FFT. Maybe you've seen that in the literature. And FFT stands for Fast Fourier Transformation. And why is it called that? It's simply called that because a guy named Joseph Fourier, a French mathematician back in about 1800, he was playing around with stuff. I think there were just reruns on TV, and so he figured, well, I want to do something different. And so he was trying to figure out, how does heat transfer through a solid? Maybe he burned his hand on a pan making lunch. So he was doing that, and he realized that any type of a periodic waveform can be created using a fundamental and these harmonic sine waves. And by doing that, it's so much easier to solve his problem. He solves it with one sine wave at one frequency, and he solves that problem with the second sine wave at 2 times the frequency, and the third sine wave at 3 times the frequency. And solving those with just a single sine wave was easy to do. Then all you do is add the solutions together, which is that superposition principle, and he comes up with the final answer. And he said, hey, this is cool. And you could do that. You can do that on a napkin at a dinner table tonight, if you want to. But it wasn't until really 1960 where a couple of guys who were working for IBM, their names were Tukey and Cooley, and they were doing Fourier transformations, and they say, you know, this is really tedious stuff. They said, well, duh, hey, we work for IBM. We got a computer here. Now, true, it was the old IBM 360s, you know, with tubes and stuff like that in it, but they came up with the program, and it's so much faster doing it that way, they called it a fast Fourier transformation. So that's what the FFT is. But what it does is you put in that red waveform, you know, you type it in on those cards. Remember those cards? Some of you do. All right, good stuff. All right, you type it in on that, and then you put that through the computer, and it comes out with a table like this, saying that red waveform is made up of a fundamental, which has this peak, this RMS, and 0 degrees. Third harmonic, there wasn't any third harmonics in there. There was a fifth harmonic with this amplitude, that phase angle, seventh harmonic with that amplitude, that phase angle. No ninths were in there, the 11th with that and that. Those were the ones we were looking at. And here's all those other harmonics which I added in there later on. But now that we have a table like that, we can now do some things. For example, if we wanted to find out, well, what is the RMS value of that blue waveform, all those harmonics together? And what is the RMS value of that red waveform, where you've got the harmonics and the fundamental together? Well, now that we have some numbers, we can actually figure that out. And the way you figure that out is, well, here's another way to display it. Instead of having a table of numbers, you can display it as a spectrum. And this is real nice because it's more visual. You can sort of see what's going on. And sort of keep in mind that as the frequencies go up, the amplitudes usually go down. And so the larger amplitudes are for the lower frequencies, and then they drop off like this. But here's what you do. To find that blue waveform RMS value, what you have to do is you don't take the 27 amps and the 11 amps and the 5.5 amps. You don't sum these guys up. If you do, you'll just get the wrong answer. What you have to do is take the square root of the sum of the squares, and that's what RSS stands for, the root of the sum of the squares. So that means you have to take this number, square it, take this next one and square that, take this and square it, take that and square it. And as you can see, Excel does an excellent job of squaring numbers. And so then when you add all these up, then you get this number, and then you take the square root of that, and that tells you that, aha, that blue waveform, all those harmonics, has an RMS value of about 31 amps. Now, we were eyeballing it, and we figured it was around a little less than 35 amps, so our eyeballs weren't too far off, but it wasn't as accurate, certainly, as this. So we have about 30 amps or 31 amps of harmonics. We have about 70 or 71 amps of that fundamental waveform. Remember, that's the one that had a peak of 100 amps? And now, when we add those together, what's the RMS value of that red waveform? Again, you don't take 30 and add that to the 70 and it's 100 amps. You have to do the square root of the sum of the squares again. And so we can do this ourselves here. We don't need a slide rule. We don't need calculators or our phones. What's 30 squared? 30 squared is 900. All right, good stuff. And what's 70 squared? It's getting a little harder. You didn't know there was going to be math, did you? Yeah. All right, so 4,900. So 900 plus 4,900 is 5,800. And remember back in 11th grade, the square root table, so the square root of 5,800 is Yeah, somewhere around 77 amps. So that's what a true RMS ammeter would measure if you're measuring that red waveform. It would measure 77 amps. But that 77 amps is made up of 70 amps of fundamental and an additional 30 amps of harmonics. That's how you get to that 77. Now, we get something else also with this. We take a look at the ratio of those harmonics to that fundamental. 30 divided by the 70, that tells us what's called the THD. And what does THD stand for? That's a total harmonic distortion. In other words, how badly distorted is that red waveform from a pure sine wave? And so we get a number here of about 43%. So there's a couple of things here which are really key in understanding harmonics. The first is that the THD is not just a number that sits by itself. It's a ratio of two numbers. So if somebody tells you, hey, I just measured my current, I got a THD of 50%. Say, well, okay, but is that really a problem? Well, how much is the fundamental current? How much is the other current? You need to know one of the other pieces to it. Just knowing that the THD is 50% doesn't give you the whole picture. It gives you a piece of it, but not all of it. So a key thing to realize, again, is that the THD is the ratio of your harmonics to your fundamental. That ratio. So that means there's two ways of reducing the THD value, right? You reduce the THD value by keeping the fundamental the same and reducing the harmonics. That'll do it. Or, even if you don't change the harmonics, if you increase the fundamental, that will also reduce the THD. It's good to know both of those things. Sometimes you need that in the back pocket to be able to make a... I didn't do that. All right, so we can do that. So sometimes I get a question, okay, why do Dries produce harmonics? I mean, what are you guys thinking, you know? Why do you do that stuff? And the reason why is it's really part of that rectifier section where we take the three-phase AC and we convert it to DC. When we do that conversion, that's when we see a waveform that no longer looks like a sine wave. And when you analyze that waveform, you see that that waveform contains harmonics. So that's really what's going on there. So if we were to take a look at this, here's our diode bridge. We've got our three-phase coming in. We'll take a look at the line current, our voltages, our voltage here on the capacitor. And this is what things look like for that particular system. And we zoom in on it. And what you'll see is that the only time current will flow is when the line-to-line voltage exceeds the capacitor voltage. So here's our line-to-line voltage from phase A to B. And here's the line-to-line voltage from phase A to C. And only when that's exceeding our DC bus capacitor right here, that's when the diode is forward biased and current can flow into the capacitor. The rest of the time, the diode says, hey, you can't go. And so no current flows. And so right here, isn't that cool? So right here is when the current can increase. It's because the line voltage exceeds the DC bus. And right at this point, it's no longer increasing. And then it drops off fairly quickly after that. And then nothing happens until this next time comes along here. In this system, there was very little impedance in the system, very little inductance anywhere in the system, in the transformer or in the cables or anything else like that going to the drive. So the rate of rise of the current is fairly fast. It's like 400 amps per millisecond. So keep that in mind. And here's what's happening. The first pulse there is power's coming from phase A, around here through charging up the capacitor, going out through phase B. And the next time, second pulse coming in phase A, around here, out through phase C. So that's why it has two pulses. And so the wave shape is simply because of what we're doing. And again, when we analyze that wave shape, you see it has these harmonics in it. Now, if we put some inductance here, or if we put some inductance there, either place, that current's going to have to flow through that inductor. And when current tries to flow through an inductor, it cannot change as rapidly as it could without the inductor. It's going to slow down the rate of rise of the current. So it's going to change the shape of that current waveform. And this is what it's going to look like. So again, if we zoom in on here, we see, again, it rises while the line-to-line voltage exceeds the capacitor voltage, but it doesn't rise as fast. The rate of rise here, instead of being 400 amps per millisecond, is only 80 amps per millisecond because of the inductance that's in the circuit. So we've changed the shape of the waveform simply by changing the components that are in that circuit. Sometimes I get this question: why do the line currents contain fifth and seventh harmonics? And there's a secret reason why. The reason why there's fifth and seventh harmonics in there is because. Because what? Well, yeah, it's just because. It's not like it's trying to produce fifth harmonics or seventh harmonics. It's there because that's what the waveform looks like. And when you analyze that waveform, you see, hey, there's a fifth harmonic in there. And there's a seventh harmonic. But there's no third harmonics in that waveform. And there's no fourth or sixth harmonics in there. There's some other higher frequency stuff. But it's simply because that's what the waveform looks like. And the waveform looks that way because of the circuit we have. Well, are there any other times where you might see some other harmonics, like a third harmonic? Yeah, you can. For example, what if you take a look at the current going into your computer power supply? It would look like this. You have single phase right here because most of us don't have three phase at home. I was hoping I could get three phase at home. But the power company says, boy, that's going to cost a lot, you know. And so I said, well, okay, I'm kind of cheap, so no, I'll live without three phase in my garage. But anyways, for a single phase, all you have is just two lines coming in. All you need are 4 diodes. You have a capacitor, and then inside that little box for your power supply, they've got like a switch mode power supply that gives the 20 volts or the 5 or whatever you need after that. But if you take a look at the current right here, here's what it looks like. It comes along here, and you get a bump, and nothing, and another bump, and nothing, and another bump. And again, that bump occurs when the line-to-line voltage exceeds the capacitor voltage. But you just get a single bump. You don't get those two bumps there, those two humps. And so when you analyze that, what you see is got third harmonics in there, and the 5th and 7th like before, but also the 9th, and 11th, 13th like before, and also the 15th. So it now contains what's called triplet harmonics, multiples of 3, which were not there before. But you still notice that this really, well, you sort of forget about these, but this really doesn't have much in the way of even harmonics. Is there any time where you might get even harmonics? And yes, there is. I'm glad you asked. I've got 5 minutes? Okay. Roughly. Maybe we'll make it 10. Suppose you have a diode right here that sort of became smoke, all right? It no longer is there. That's an open part of the circuit. If you take a look at the current that's coming in here now, this is what it looks like. You get 2 bumps here part of the time, and 0, then just a single bump over here. So it's sort of like a mix of that single phase and the 3-phase type of current. And when you take a look at the spectrum, you can sort of like see the fingerprint of that 3-phase with that 5th and 7th, 11th and 13th, 17th and 19th. You see that there, but you also see some third harmonics. You also see some second harmonics. So usually, if there's even harmonics, that means there's a problem someplace. You really don't want to see even harmonics in your system. Now, while you're here in Chicago, you know, you go out, you eat a nice big dinner, and you get back to the hotel room. You're really full. You don't want to go to sleep yet because you know, you're just too full. And so instead of just doing some searching online, what you should do is go to this website, falstad.com, and what you can do is you can create your own waveform. Isn't that neat? So you can create your own waveform, and not only that, but you can turn on the sound of your computer, and you can hear what it sounds like. You say, well, what does that really sound like? It has the sound associated with it. And if the sound is up a little bit too loud, you'll hear a banging on the wall, and that's the guy in the next room saying, turn that thing down, right? Okay, put on your headphones and listen to it. And you can make any type of waveform you want to with this thing. It's really a lot of fun. You'll be up, I guarantee, up till 2 a.m. playing with this thing, and you look at your watch and say, man, what have I been doing all this time? But it really is a lot of fun. So then the question becomes, okay, well, so what if my drive draws these current harmonics? Really, so what? What's the big deal? And here's where the big deal comes in. These current harmonics produce voltage distortion. So this is the second key thing here. The first key thing was, remember the THD, that total harmonic distortion, is a ratio of your harmonics to your fundamental. And the other thing is this piece right here, that those current harmonics cause voltage distortion. And I'll show you what I mean. Suppose I have a 1500 kVA transformer. It's a transformer about this big, about this tall. I was shopping with my wife at a mall near our house, and as we were going to our car, I saw there's a transformer over by the side. And I said, just a minute, I want to take a look at the transformer. She said, why? I said, well, I want to see how big a transformer is required to power a mall. Aren't you curious? I said, no. Well, that's too bad. I am. And so it turns out to be about 1500 kVA. So now, if you're at some sort of party and somebody needs a piece of trivia, you can tell them, hey, it takes about 1500 kVA to run a mall. Did you know that? Well, I don't, maybe they'll ignore you the rest of the party. But anyway, if you have that size transformer, and suppose we have a 75 horsepower drive on it, here's what's going to happen. The currents are going to look like this, similar to what we were seeing before. The voltage is going to be slightly distorted. You see a little bit of notching right there and right here. So there's about 1% of distortion in the voltage waveform, about 37% distortion in the current waveform. If we put that same drive on a smaller transformer, say a 75 kVA transformer, that's only this big, then what's going to happen? Well, here's what's going to happen. The current waveform is going to be about the same. Actually, it's going to be improved in terms of its distortion. There's more inductance in that transformer. And so instead of being 37%, it's actually improved to 29%. But look what happened to the voltage waveform. It's kind of really ugly looking. There's almost 10% distortion in the voltage. And so that means every other piece of equipment attached to that same transformer has to live with that voltage distortion, and that's where the problem is. Now what we call this flat topping, because the tops are flat, kind of flat. Now the bottoms are flat too, but we don't call it flat bottoming because that just sounds rude. So we call it flat topping. All right, so these are the types of problems that have come about then with respect to harmonics. With respect to some of that current that's in those harmonics, the transformer has to supply those currents. So that means instead of supplying just 70 amps of fundamental current, it has to supply 77 amps, 10% more current, simply because you've got those harmonics in there. And not only that, but those harmonics are higher frequency, so that means there's more eddy current losses in the transformer, which means more losses in the transformer because of that. Let's see, what else? You might need larger wire sizes, especially if you have a whole bunch of drives, because they have to carry more current, 10% more current. Increase in utility costs because the power factor is poor. You might get some extra zero crossings with certain types of rectifiers, not with diodes, but with an active front end you might. And power factor correction caps might have a problem with this stuff. And so then the question becomes, how much is too much? And I suppose we're getting close to time, but you don't have to go anywhere, do you? They don't have to go anywhere. Any questions so far? No questions yet? We're okay? Can we keep going? Another 5 minutes? Okay, I have another 100 slides. If you like, drop me an email or something like that, and I'd be happy to send this to you so you can look at it at your leisure. But how much is too much? Well, IEEE got together, and they put together a standard called the IEEE 519. They had a 1982 or 83 version. They had a 1992 version. And just this year, finally, in March, they came out with a 2014 version. For the most part, it's the same. And this is a recommended practice. They're not saying if you follow this, you won't have any harmonic problems. What they're saying is if you follow this, you're less likely to have harmonic problems. And if you do have harmonic problems, well, you still have to solve them, but it's not as likely. And so they have some tables in there, tables that talk about voltage distortion, because that's the key thing, is the voltage distortion. That's what you want to keep low, is that voltage distortion, because that's what affects everybody. And there's some machines that might not work well if you have 10% distortion on that voltage. That's where that problem is. It's not because this drive is drawing so many amps or something like that, or has 37% current distortion. It's what's that doing to the voltage, and how is that affecting other pieces of equipment. They also have this other table here about the current distortion, because that's what causes that voltage distortion. And they also talk about when you take these measurements, they tell you where to take the measurements, under what conditions. Do you take it at full load? Do you take it at no load? You take it while things are accelerating, decelerating? Under what conditions? And it's really under maximum load conditions is where you take those measurements. And the point where you take them almost always is really where the power comes into your plant. Not in front of the drive, but really at the power coming into your plant. That's what they call the point of common coupling, because it's common among other customers. Because they don't want you to turn on a machine here, and it causes the time clocks in the plant next to you to go fast. I got to wrap up. All right.
We really need to finish. I think they're closing us down.
So I really got to finish. All right. So tell you what. Anyway, so what this is talking about is really how, under what those conditions need to be for taking those measurements. Let me go to end. Here we go. In here, it does talk about multi-pulse solutions, how they work. It talks about other types of filters you can put on in front of a drive in order to improve the harmonics. And if you want to get hold of me, you can give me a call, write me, drop me a note right here. I'd be happy to send a copy of this to you, along with all these cool pictures in there. All right. Any other questions?
I really think we have no time for questions. So I thank you very much, ABB. I failed to mention that you're principal engineer for ABB,
yeah,
like an independent one. And to you, Rick, for this very educational presentation. I really love it. I hope we have time to run through it completely. But, you know, Rick has been kind enough to give us his email and contact details. So any question you can address directly to him. Thank you very much, Rick. Thank you very much.